For decades, astronomers could only watch the universe. Now, thanks to observatories like LIGO, we can listen. When massive objects collide, they send out gravitational waves, ripples that stretch and compress the geometry of space. These detectors are tuned to the sound of black holes merging. But there is a theoretical suspect hiding in the data: the traversable wormhole. From the outside, a wormhole exerts the exact same gravitational pull as a black hole of the same mass. The difference is entirely structural. A black hole ends in an event horizon, an absolute point of no return. A wormhole pinches down into a traversable throat, a physical tunnel connecting to another region of space. Because a telescope cannot distinguish between the two, we have to look for the discordant ripples they leave behind. Catching a wormhole requires a forensic search for the subtle mathematical anomalies hiding in our gravitational wavelogs. Imagine a solar mass black hole caught in the gravitational grip of a massive wormhole. As it loses energy, it spirals into the larger object. If the primary object were a black hole, the final moment of that collision would trigger a massive, sudden spike in gravitational waves. Physicists call this a chirp. If the target is a wormhole, the wave signal drops out as the black hole crosses the throat. Emerging on the other side produces a decreasing frequency, an anti-chirp. The black hole swings back and forth, generating a repeating, decaying loop of chirps and anti-chirps. Discovering this specific rhythm of rising and falling frequencies would tell us the incoming object didn't crash into a singularity. It survived passage through a space-time tunnel. We can also learn about an object's structure by seeing how it reacts to a perturbation. When a standard black hole is struck, it vibrates, producing a brief signal called a ring-down that quickly fades into silence. A wormhole reacts like a chamber, its throat acting as a double potential barrier. Gravitational waves get trapped, bouncing back and forth. With every bounce, a fraction of energy leaks out, creating a distinct train of periodic echoes long after the initial impact. If the wormhole is asymmetrical, trapped waves can steal energy from its rotation. Through superradiance, the echoes amplify, getting louder over time. Detecting these delayed, repeating pulses following a collision unmasks the imposter. An event horizon swallows energy entirely. Echoes require a physical structure to bounce off of. To find the final clue, we look at the absolute extreme: a supermassive black hole consuming a microscopic zero-length wormhole. This collision forces a glitch in spacetime called a causal island. It's a region buried inside the large black hole that temporarily maintains causal contact with the outside universe. The island rapidly shrinks and disappears, cutting off the communication channel forever. Receiving any data transmission from within the boundaries of a black hole is the signature of a collision that moves beyond the limits of general relativity. The evidence board is complete. We are hunting for the gaps of the anti-chirp, the repeating pulses of a trapped echo, and the brief transmissions of causal islands. Physicists are currently embedding these exact parameters into the search algorithms of our existing gravitational wave observatories. Future third-generation detectors will feature vacuum tubes stretching for miles, providing the sensitivity needed to scan for these microscopic data anomalies at much higher redshifts. Extracting just one of these discordant signatures from the noise would confirm the existence of negative mass exotic matter, proving that spacetime can indeed be bridged by physical tunnels.